Kia ora team, welcome to the video here on question 5 of the 2017 SCOL exam. We start off with a trig identity, which is an absolute beast. It's going to require quite a bit of work to get through. And then the second part is a sequence, kind of like the Fibonacci sequence, just a little bit different with the factor of a half. Okay, so first up, I'm going to show you a couple of ways to do this first one. What I like to do when I'm doing the SCOL questions myself, particularly with messy trig identities, is to work on a double spread page. And I do like all my messy working on the right hand side in the margin, and then my proof follows really nicely on the left hand side. Okay, so cos to the 5 theta, cos 5 theta, not to the power. On the formula sheet, there's a whole heap of formulas to do with there's cos 2 theta. Cos 2 theta is equal to 2 cos squared theta minus 1. It's a double angle formula. We can make that cos 4 theta. Cos 4 theta would be just 2 cos squared 2 theta minus 1. Notice there, if you double the angle, you only double the angle. You don't change any of the other stuff in the formula. And there's also one that's cos of a plus b, the compound angle formula, which says that this is true. And this is the one that we use to start this problem off, because 5 is obviously not an even number. So what we do is we say, let that equal cos of 4 theta plus theta. Okay, we split the 5 theta, and then we can let a be 5, not a be 5, a be 4 theta and b be theta, and that's our starting point. So we've got cos 4 theta cos theta minus sine 4 theta sine theta. And now I look at the right hand side and where I'm aiming. In the right hand side, only thetas. There's no double angles or anything else. There's just powers, and there's no sines. It's only cosines. So that's giving me a bit of direction. Okay, I use the double angle formula again for 4 theta. Okay, so it's 2 cos squared 2 theta minus 1, all times cos theta. And then the sine 4 theta one, I don't have any options for that. The double angle formula for sine is 2 sine cos. So sine 4 theta is 2 sine 2 theta cos 2 theta. It is a common mistake that students make, but if I double the angle, I just double the angles. I don't change the 2 there, it stays as a 2. That's part of the structure of the identity. Okay, so sine 4 theta is going to be 2 sine 2 theta cos 2 theta, and then we've got an extra sine theta I haven't dealt with yet. Okay, and then this cos squared 2 theta term, what that actually means is cos squared 2 theta is the same as cos 2 theta all squared. We just put the 2 on the inside because it's tidier. So what we have there is 2 multiplied by cos 2 theta all squared. Cos 2 theta is this dude. So that goes in, and I need to square it. I've got minus 1 really easy here to make mistakes. What am I doing with brackets? That's the cos 2 theta thing all squared. There's a 2 in the front of it, minus 1 after it. I was right, I just looked wrong. All times by cos theta minus I'm going to do the next one on another line because I'm going to run out of space otherwise. Got minus 2, the sine 2 theta thing. I need to change that to 2 sine theta cos theta. And the cos 2 theta, I need to change that to 2 cos squared theta minus 1. And then I've got another sine theta. Alrighty. Then we expand out some of the brackets. So the first stuff is expand the internal brackets, these ones. Expand that first, then times everything by 2. So we've got 4 cos to the 4 theta times 2. And then we've got minus 4 cos squared times 2. And then we've got plus 1 times 2 minus 1, all times by cos theta. That's the first line done. And then the second one, I've got a sine theta at the end of it here. I'm just going to sneak that in as a sine squared in that front factor, so I can get rid of that. Makes expanding a little bit easier. So we've got, when we're expanding, we've got minus 2 times 2 sine squared cos times 2 cos squared is the first term. So minus 8 sine squared cos cubed. And then the next part of the expansion, minus 2 times 2 sine squared cos times minus 1. So it's minus plus 4 sine squared theta cos theta. Fortunately, there is an easier way to solve this problem. It just requires a bit of extra knowledge of complex numbers. Okay, and then we expand out that top line again. So we've got 8 cos to the 5 minus 8 cos cubed plus cos theta minus 8 sine squared needs to be replaced as 1 minus cos squared. Do that again there, 1 minus cos squared. And the identity I'm using is the Pythagorean Pythagorean identity, sine squared plus cos squared equals 1. Okay, and then do a bit more expanding, 8 cos to the 5 minus 8 cos cubed plus cos theta minus 8 cos cubed. I'm lining these up now, plus 8 cos to the 5 plus 4 cos minus 4 cos cubed equals 16 cos to the 5 minus 16 cos cubed. Oopsies, not 16, 20. Gosh, when basic maths lets you down. Plus 5 cos theta. And I haven't looked at the right hand side in a while. Yippee yay, it's it. So when we prove it, put a box there, smiley face inside the box. Okay, that was really intense. But in a scholarship exam, when there's 2 parts, if there's a part A and a part B, you're looking at about 15 minutes per part. So I would have said, give ourselves, 8 to 10 minutes to do that. I don't know what the video timer is, but hopefully we're doing well at this stage. Okay, on a side note, I'm going to show you a different way of solving that because that was really intense and there is a quicker way. So let's just do this on the margin. Okay. If you've done past school papers, you would have seen this potentially in the answer schedule, but it uses the idea that if you take a complex number z, which has a modulus of 1, so we can write that as cos theta plus I sine theta in polar form, often shortened to cis theta. If I power z by 5, I've got 2 ways of doing that. I can power this by 5, or I can power that by 5. Now the first one requires us to use binomial theorem. Binomial theorem, when we're expanding something like a plus b to the 5, we write the coefficients of Pascal's triangle out. If this is completely new to you, then search up Binomial Expansions. It's a little bit of extra stuff. So we've got 1, 5, 10, 10, 5, 1. They're the coefficients. And then we take the first term, power it by 5, 4, 3, 2, 1, and then 0 for the last one, which we don't bother writing. And then the last term, b to the 5, b to the 4, b cubed, b squared, b to the 0, which we don't put. And just separate these with pluses. Okay, that's how you expand a binomial really quickly. So let's move that up there. So for z to the 5, because we've got cos theta plus I sine theta, again we z to the 5, we write out the coefficients, 1, 5, 10, 10, 5, 1. We start off with the first term, cos theta to the 5, which is cos to the 5 theta, cos to the 4 theta, cos cubed theta, cos squared theta, cos theta. I'm going to run out of space. This is definitely easier because if you're quick with binomial expansions, it will be. Then the last one, I sine theta to the 5, I sine theta to the 4, I sine theta cubed, sorry I'm getting really messy here team, I sine theta squared, I sine theta, and then I sine theta to the 0 for that one, plus, cool. Now, if we go back to cis theta to the 5, and we power that, de Moivre's theorem tells us that if z is r cis theta, then z to the n is r to the n cis n theta. That's a fundamental of complex numbers. So what that tells me is that z to the 5 is just equal to cis 5 theta, which is cos 5 theta plus I sine 5 theta. Okay, they're both expressions for the same thing. Lastly, what we do is go, we wanted this dude, cos 5 theta. It's the real part of z to the 5. Okay, it's the real part. So we go through the expansion in the binomial theorem and we go real. I know it looks like it's got an I in it, but it's I squared, and I squared is -1. And then this dude here is real because I to the 4 is equal to 1. So, therefore, cos 5 theta is equal to cos to the 5 theta plus 10 cos cubed. It's actually my bad, it's minus 10 because of the I squared, sine squared, and then it's plus 5 cos theta sine to the 4 theta. And all we're left to do now is get rid of the sine squareds. Cos to the 5 theta minus 10 cos cubed, sine squared is 1 minus cos squared, and then we've got 1 minus cos squared for the sine to the 4, sine squared squared. Okay, and if you expand that out, and I'll let you test it, it is actually going to give us the same identity we had before. Alrighty. Second part. Find a polynomial in terms of cos theta with roots of cos 2 pi over 9, cos 4 pi over 9, and cos 8 pi over 9. Hint, find the general solution of cos 5 theta equals cos 4 theta. Okay, so these questions are connected. So often there'll be a relationship between them. In this case there definitely is, because we've got cos 5 theta equals cos 4 theta. So I don't know quite how that connects at this point, but it's saying start there. There's two ways to solve this equation. Number one is to realise that this is, they've used a poor choice of variable, but on the formula sheet, it tells you that if cos theta equals cos alpha, then the solution is theta equals 2n pi plus alpha, or plus or minus alpha, 2n pi plus or minus alpha. So we don't have theta, we have 5 theta, and we don't have alpha, we have 4 theta, but we can still use this formula. We just say, therefore 5 theta equals 2n pi plus or minus 4 theta. And there's two cases, just like there is in the quadratic formula, there's a plus and a minus. So if we take the plus, we've got, it's 4 theta on the right, move it to the left, it will be theta equals 2n pi. And think about, n is an integer, so we've got, 0, 2 pi, 4 pi, la la la. We've also got negatives. If you take the negative root, then you've got, it's minus 4 theta on the right, which makes 9 theta on the left. So it'll be 2n pi over 9, which gives you 2 pi over 9, 4 pi over 9, 6 pi over 9, 8 pi over 9, etc. And that's the connection between the hint and the thing we're trying to do. It says here 2 pi over 9, 4 pi over 9, and 8 pi over 9. Okay, so we're on the right track. But it does ask us for a polynomial, and we definitely don't have that. We had a linear equation. This here is a linear equation. So, starting again at this equation, but this time use the identity that we proved at the start. So if you go cos 5 theta is 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta, that's the left hand side, equals, and we need a similar formula for cos 4 theta, but fortunately cos 4 theta is a little bit easier to work with because it's an even number. I'll let you fill in the details here. I'm just quickly loading up Wolfram Alpha. So if I type in on Wolfram Alpha cos 4x, it's going to give me a equivalent polynomial. It will just be a degree 4. Might have to scroll down a little bit to get it. Yep, it tells me that it's 1 minus 8 cos squared plus 8 cos to the 4. Maybe you could try the binomial theorem and the Moivre's theorem. Of course, I've got to have thetas. Okay, so that's our polynomial that we're trying to solve. And if we rearrange that, it's easy, we go with the 8 cos theta, cos 4 theta first, cos to the 4 theta, alright, that's a para 5 equation, and remember we've already got the solutions to this, okay, we already know what theta is, so if I let at this stage let u equal to cos theta, then I've got 16u to the 5 minus 8u to the 4. It makes it a little bit easier to work with. Okay, now what you need to realize is that one of the solutions to this was theta equals 0. Okay, theta equals 0 is a trivial answer because cosine of 5 times 0 is the same as cosine of 4 times 0. And if theta equals 0 is a solution, that gives you u equals 1. So we know theta equals 0 is a solution. cos 0 equals 1. So u equals 1 is an answer. So that means that this thing here, u is equal to 1, is a solution. You can check that real quick. 16, take away 8, minus 20, plus 8, plus 5, minus 1. Yep, that equals 0. So we can factor it out. I'm just factorising by inspection here. I've got 16u to the 5 minus 16u to the 4 plus 8u to the 4 minus 8u cubed minus 12u cubed plus 12u squared minus 4u squared plus 4u what was the last thing I had? I had a minus plus 4u plus another u is plus 5u, and then the last term is minus 1 times 1. Right, so it does factor. That's quite tricky actually. But what I did is I went through each of the terms and made sure that they worked in order. Okay, so that was theta equals 0. We knew that was a solution. We also know that theta, and this one's a little bit sneaky, 6 pi over 9. 6 pi over 9 is the same as 2 pi over 3. Okay, so we also know that theta equals 2 pi over 3 is a solution, and that's cos of 2 pi over 3. If you work that one out, it's a special angle. Cos of 2 pi over 3 is negative a half, and so that's u equals negative a half, which is the same as 2u plus 1 equals 0. So that is apparently a factor. I'm using the factor theorem. The reason why I went to that 2 pi over 3 or 6 pi over 9 one is because that's the other one that's not listed in the question. See how in the question it's 2 pi over 9, 4 pi over 9, and 8 pi over 9. It skips the 6 pi over 9. Sneaky. So we now need to factor this quartic equation with 2u plus 1 as the remaining factor. So u minus 1, 2u plus 1, and this will be 8u cubed. What I'm trying to do is I'm trying to make this out of this. So I've got 16u to the 4. I've now got 8u cubed, and I don't need any more u cubed. So I don't need any u squareds in the next thing. I need to make a minus 12u squared. So I've got minus 6u. So what have I made so far? I've made 16u to the 4 plus 8u cubed minus 12u squared minus 6u. I need to add 1 there because that will add 2u, and it also gives the plus 1, so that works as well. So that's the factorization, and that is the polynomial we're looking for. So what means, therefore, 8u cubed minus 6u plus 1 equals 0 has 3 solutions, and the solutions are cos 2 pi over 9, cos 4 pi over 9, and cos 8 pi over 9. If you don't believe me, solve that cubic on the graphics calculator using the polynomial solver, and then evaluate those 3 trig expressions, and you'll find that they're the same if you're in radians. Now the question, if you look at the mark schedule, is a little, I think the question's actually a bit wrong, because they said find a polynomial which has solutions of cos 2 pi over 9, cos 4 pi over 9, and cos 8 pi over 9. And then what they do in the answers is they replace the u's, they put them back as cos, so they give an answer of 8 cos cubed theta minus 6 cos theta plus 1 equals 0. Now this polynomial has solutions of theta equals 2 pi over 9, 4 pi over 9, and 8 pi over 9. It doesn't have the cosines, so I believe that my answer is correct, and their one not correct, but I'm sure they've probably accepted both. I'm just going to check that because I'd hate to be wrong after such a long part of the video. Let's have a look. Question 5 is usually the hardest, so that was pretty intense. What have we got? 8 cos cubed minus 6 cos theta plus 1. Brilliant. Okay, then the part B of this gives us an interesting sequence. And I've said in an earlier video, if you've got an unfamiliar sequence, just play around with it and see if you can spot some patterns. So we've got the first two numbers, 2 and 7, and then the next term is found by just taking a half of the sum, in other words, the average of the last two numbers. So let's go. Let's just keep a record of this. N. What is they start with n equals 1, they go 2, n equals 2 is 7, and then n equals 3, the next one is the average of the previous ones, working for fractions. It might make it easier, but I'll start with decimals and see how I go. Okay, then for the fourth one, I want to take those two terms and average them. 5.75. 5. 5.125. Maybe 6. Just one more. Let's see if that helps us establish a pattern. Normally with sequences you explore the differences. So if we look at the differences between this, we can see that they're not going up by the same amount each time. So that rules out a linear pattern. Let's have a look. Differences. Difference of 5. Difference of minus 2.5. Difference of 1.25. Difference of minus 0.625. Difference of positive 0.3125. Okay, so the differences are actually halving, and then they've got this alternating factor of plus minus. So if I wanted to find let's say the second term, I already know the second term, right? So 7. But if I want to find the second term, I would write 2 plus 5. And then the third term is 2 plus 5 minus 2.5. And then the fourth term is 2 plus 5 minus 2.5 plus 1.25, etc. So I'm using the differences to get the next value as opposed to finding the previous two values, adding them and dividing by 2. So a to the n, the nth term, is always going to have a 2, but then this dude, which changes, is a sum, given this notation, sum, and we need a general term for that. So the first term of that sum is 5. That's often given the letter A. And the ratio of the terms is minus a half, and it's a geometric series. If you've never seen geometric series before, they're taught in level 2, NCA level 2. Search up geometric series because there is a formula for them. The sum of a geometric series, actually I think, the question gave it to us, didn't it? Now, they gave us 4 formulas and then just said like they could be useful, so we have to realise that this here is a geometric sequence and this is a geometric series, and I'm not too sure about the notation because I use different letters. So what I'm going to do is try and work out what this notation means first and how it applies to my sequence. So Sn is T1, apparently, do this in the margin, Sn equals T1, what was it? I should know this off by heart, I've used it heaps, but 1 minus r to the n over 1 minus r. You can actually prove this quite easily, but don't have the time for that. This video is already long enough. Okay, so T1's 5. And this is going to be a little bit confusing because this first one here is actually A2, and so our ends are not gonna match. T1 is 5, and then the ratio is -1/2. So let's just see what happens if for this formula, if I put in n equals 1, let's see what I get. Oopsies, it's 1 minus -1/2. Okay, so I've just put in n equals 1. Let's see what we get. 5 times 1 minus -1/2 divided by 1 plus 1/2. That comes out as 5. Okay, which is exactly what we wanted for that first sum. Let's just test it if I change that n to 2. That gives me 2.5, which is great. That's the second row. That's 5 minus 2.5 is 2.5. I'll just try it one more time just to get my head around it. So I change the 2 to a 3, and it gives me 3.75, which is the third row, 5 minus 2.5 plus 1.25. Perfect. So that sum that we're wanting to add and remember it matched when n was 1, it gave me 2. So I'm not going to bother with that summation notation. I'm going to go straight to the 5 times 1 minus -1/2. This is where I've got to be careful. When I made n equals 1, I got the first one. So, but A2, that was A2. So I want to go n minus 1 there. All divided by 1 minus -1/2. Cool. So that's the general formula, and then the last question says, what happens to this sequence, which is interesting. It's a sequence, but we actually worked it out using a sum. What is the limit as n tends to infinity? So actually you can play around with these numbers, right? We've already got up to 6, and we can see it's kind of converging to something. It's still bouncing around a little bit, but it's not going up and down by as much. So if I go limit as n tends to infinity of an, I just need to think, well, what happens when n goes really, really large? -1/2 to infinity, or you can just put in -1/2 to the power of like a really big number in the calculator, and you see it goes to 0. So we end up getting 2 plus 5, just lots of 1 over 1 plus a half. And when you work that out, you end up getting 5.33333, or 16 thirds. Right? So kind of looks right. But if you just find a few more terms in your sequence, you'll find that it is going towards 5.333, and it gives you confirmation. Now that was a really, really tricky question. Question 5 as a whole was really, really nasty. But when you make progress in trig identities, you pick up marks. And if you played around with that sequence a little bit and found a few terms, you'd get at least a mark. So just encourage you to, even with a tricky problem, to just get it started. See you in the next video.